Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Good afternoon, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams. And to pick up where we left off in previous episodes, where we discussed exoplanets, today I want to introduce a person who, in astronomical circles, really needs no introduction. Today my guest is Charles Beichman. He is a senior faculty associate in astronomy at Caltech, and he's the executive director of NASA's Exoplanet Science Institute. Dr. Beichman, welcome aboard.
Well, great to be here.
So, you have a very, very extensive career of studying exoplanets, and also kind of like you to brag a little bit for my listeners, given all the work that you've done. Can you tell us a little bit about your dossier, your background here?
Yeah, well, I've always been interested in, sort of the philosophical basis for looking for planets outside the Earth. I actually started off in college as a philosophy major and figured that astronomy would do a better job at answering some of these questions. So I started out working in what was then the nascent field of infrared astronomy, looking for stars in the process of formation. First, very massive bright stars, and then as our sensitivity got better and better, particularly when we moved into space with the infrared astronomical satellite, looking for stars like our own sun in the process of formation. So in the mid-'80s, I was privileged to work on the infrared astronomical satellite, which was an international effort to survey the sky in the infrared. And that was very successful, and we started identifying what we'd call protostars, stars like the sun, collapsing, forming in collapsing clouds of gas and dust. And a very interesting aspect of them is the material surrounding them was located in a disk of material. And that disk is where material from the outer cloud would collapse onto this rotating disk and fall into the star. But it very naturally gave rise to the idea that that's where planets would form. And that was really the beginning of a long and very fruitful path in science to follow the formation of disks, to form planets and stars, the formation of debris disks left over from the formation, and eventually we'd start to image those disks. And then a decade or so later, we started to find planets themselves. First, Jupiter-sized planets with the radial velocity technique, and then the transit technique. And, here we are today with now more than 5,000 plus planets under our belts.
Yeah, in fact, you've mentioned the infrared astronomy satellite. That was one of several missions that you worked with and worked on. You also helped with the NASA European Space Agency Infrared Space Observatory?
Yeah, there's the European, after IRAS, which surveyed the infrared sky and just said, here are all these great places to go and look at specific objects in more detail. First, ESA developed the Infrared Space Observatory that was meant not to survey, but to go and look at very specific objects that started to be of interest, galaxies, protostars, stars, everything in between. And then NASA built the Spitzer Space Telescope, essentially a more powerful, better detectors, slightly about the same size telescope, but better detectors. And Spitzer ran for 4 or 5 years with all of its instruments operating with a very cold background from a supply of liquid helium. And then for another 10 years afterwards, after the helium was depleted, with its 2 shorter wavelength channels, which could operate at a higher temperature. And Spitzer did a lot of these studies of what I was particularly interested in, these debris disks, the leftover material from the star and planet formation process, which really serve as signposts for the presence of planets, we think, in many cases. So I did a lot of work with Spitzer on that project with a number of collaborators. So around 1995, we had what we called the Annus Mirabilis, the miraculous year, when two great discoveries happened. One was the discovery of what was called the Mars rock, which was a Martian meteorite collected on the Earth in Antarctica, which was claimed at the time to give evidence of microbial fossil life. That probably turned out not to be the case, but it generated a lot of excitement. But also the discovery of the first real exoplanet, 51 Pegasi, by its radial velocity measurements, first measured by the Swiss group. And they recently got the Nobel Prize for that a couple of years ago. And that really started the whole field of exoplanets and led to the start of a mission called the Space Interferometer mission, which was going to measure the wobble of stars, not in the line of sight, which you measure with the radial velocity technique, but X and Y on the sky. They move up and down, left to right. And to find an Earth, you had to make a very precise measurement. The wobble is the millionth of an arc second, sort of a human hair, essentially a dime at the distance of the moon. And SIM went along for quite a few years before, in the end, not getting approved for final development and launch. But at the same time, NASA went ahead with the development of the James Webb Space Telescope. And that, of course, is now in operation. And I was on one of the teams to build one of the instruments, which we're now taking full advantage of. And Webb is working spectacularly well.
Which instrument did you help develop?
There's the near-infrared camera, which was led by a team at the University of Arizona. Marcia Ricci is the PI. My particular interest was helping to build the coronagraph, which is the part of the camera that helps to block out the light of the central star to reveal, we hope, planets in orbit around the star. And so we've been using NIRCam to do that, along with many other things that NIRCam is useful for. So we've looked at a couple of the very bright stars that IRAS found to have these big, very bright debris disks, very bright infrared sources of radiation, much brighter than the star itself. It's dust and small particles heated to 100 degrees below room temperature, maybe up to room temperature, depending on where the dust is located. And that's the remnant of the Kuiper belt in our own system, where the comets come from, or dust in an asteroid belt, depending on where the material is located. And we're looking for planets that might help be sculpting those disks. And often we find with real detailed observation, you're not looking at a smooth disk, but you're actually looking at rings of material. That's been seen both with the Hubble telescope, ground-based telescopes, and with the ALMA millimeter telescope. These disks have a lot of very complicated structure, and we think that structure is due to the presence of planets in many cases, which are creating gaps in that material, possibly gaps that originally where the material fell onto the planet to make the planet, and then the planet's orbiting around inside the region on the freeway that it cleared out.
Yeah. So a quick note for listeners. The predominantly held model of planet formation, this is all consistent with nebular hypothesis?
Right. I mean, it actually goes back to Laplace in the 1700s, who said, look, you're going to have collapsing material. It's likely rotating, and that material will form into a disk. The material will flow into a central object, and that central object will turn out to be a star. So, of course, Laplace didn't have any of the data that we now have, but the idea has been around, and it's just been borne out beautifully with all the observations we've been making since starting with the 70s going forward to today, and it just keeps getting reinforced and reinforced. So it's a very robust model, and we have examples at every stage in there.
Yes, and this has been one of the benefits of infrared astronomy, isn't it? It allows us to study these disks that would otherwise be pretty hard to see.
Yeah, the star is so bright, particularly at visible wavelengths, and you're just getting sort of the scattered light off the dust, that you really can only see the very brightest disks. And there are some that are, very bright. But as you move into the infrared, the star's emission is much lower. It falls off at longer wavelengths, where the dust emission is really starting to become very bright. So once you're in the infrared, you can go sort of 1,000 times fainter to look for this wispy debris disk material. And with Webb, there'll be some images coming up in the next little while that people should look for some of the very bright original IRAS objects that will knock people's socks off.
Yeah, and to just circle back for a second to all the projects that you've worked on, you also led the initial software development for the 2-micron all-sky survey.
Yeah, I mean, sky surveys are a great way to understand what the sky looks like as you open up new wavelength regimes. Mm-hmm. So with 2MASS, which was really a ground-based project, we're able to really do one of the first all-sky surveys that both showed, all the stars in the galaxy, but found a lot of extragalactic objects. And seen by the technology of today, it was pretty primitive, but it was the first time it was done. And that led to discovery of objects we call brown dwarfs, which are essentially failed stars. If you don't get enough mass to really ignite nuclear burning in the center of the star, you just have this contracting ball of gas that slowly just cools off and eventually just becomes this very cold object floating in space. But these brown dwarfs, which are maybe just under 1/10 the mass of the sun, are quite common. And we found those with 2MASS, and we have some that are 5 or 10 times the mass of Jupiter, going all the way up to 70 times the mass of Jupiter. And above that, you can start getting nuclear burning, and you get just a faint M star. But these brown dwarfs, at their low mass end, are very good analogs to what Jupiter would look like. They maybe form in a different way, but you can study them and really learn a lot about the atmospheres of giant planets by studying these brown dwarfs. So we found those with 2MASS, and those became, in fact, a big target for study with Spitzer and now with James Webb. 2MASS also led to and laid the way for another space project called the WISE mission, which is a project to survey the sky at the longer wavelengths, sort of between the 2MASS ground-based windows you could do from the ground and the windows that IRAS looked at. And WISE has been going for, again, more than a decade. Started off as a cold mission where you'd have 4 wavelengths, long and short. Helium runs out, the solid hydrogen cryogen runs out, and the 2 shorter wavelengths have been going on, and in fact has been resurrected even after it was shut down for a while, resurrected to look for asteroids. So it's now a survey for near-Earth objects to look for things that might eventually be a danger of impacting the Earth. And NEOWISE has been going for almost a decade and has found tens of thousands of asteroids, been able to determine their temperature, their size, and that's given rise to a new project that's going on, NEO Surveyor, which will basically find everything in the solar system that could pose a threat to the Earth larger than about 50 to 100 meters. Won't find the comets, but it'll find the asteroids.
Yeah, a quick note on the abbreviations here. So WISE stands for Wide Field Infrared Survey Explorer,
right?
Which was a space telescope that was launched 2009. It's been in operation ever since.
It got shut down for a little while when the astrophysics program just sort of said, okay, we've gained everything we can gain. But then it was picked up by the planetary division who said, hey, we can really use this to start surveying for near-Earth objects. So NASA's planetary division took it over and has been running it for, almost 5 or 6 years now.
So yes, near-Earth objects, NEOs, that became NEOWISE.
Exactly.
Very fortunate abbreviation there. So it is really fascinating, just my own experience here into learning about infrared astronomy, and of course the way that exoplanet studies have exploded in pretty much in parallel. And I wanted to ask, so how far have we come? Exactly what can we do today that when you were doing this pioneering work in the 1980s, what can we do today that we really couldn't do then?
Well, I mean, there's two separate, just for infrared astronomy. I started out, working on ground-based telescopes, my thesis work in both my undergraduate work at Kitt Peak and then my work in Hawaii on the telescopes up there. You'd survey a little tiny patch of sky, smaller than a crater on the moon, just inching the telescope up, down, up, down, up, down to build up a little map. You didn't have cameras, you didn't have an array of pixels, you had a single pixel, and you just moved the telescope to build up an image. And just a teeny tiny area, and you'd say, okay, I'll look in this area because the radio astronomers say there's a concentration of molecules, so we might find a planet, a protostar there. And that'd be a star that might be 100 or 1,000 times more luminous than the sun. And that's what we could do. That was my thesis work from Mauna Kea. When I came to work on IRAS at Caltech, when we got IRAS data, we surveyed a region, the entire Orion Nebula and more, in a few hours and found thousands of protostars, some as small as our own sun. So that was the first step, because when you get into space in the infrared, you immediately are 1,000 times more sensitive than your telescope on the ground. Because you're on the ground, your telescope is warm and giving off heat. The atmosphere is either completely blocking windows, and the atmosphere is warm and giving off heat. When you go into space, your telescope is cold, it's not giving off heat. There is no atmosphere. You have an unimpeded view of the sky. And a factor of 1,000,000 means, you can do in a few seconds what would take you half a year to do, which means you're doing stuff you'd never hope to do, because you would never spend half a year doing some project. And then, so that was in the mid 80s to 90s. Then Spitzer came along, and it had a bigger telescope than IRAS, not a lot bigger, but some bigger. But it now started to have real cameras that were modest by today's standards, 200 or 300 pixels on a side. And of course, your phone today has megapixels, but we thought Spitzer's arrays were pretty cool. And then now with Webb, instead of an 85 centimeter telescope, which is what Spitzer was, we have a 6.5 meter telescope. And you gain in sensitivity by the fourth power of the diameter of the telescope and how fast you can go. So 6.5 divided by 0.85 is like 7 to the fourth power. That's 3,000 times faster, easily. And then instead of 256 by 256 pixel array cameras, we have 2,000 by 2,000 pixel array cameras. And in the case of NIRCam, we have 10 of those. So you've got, another 10,000 factor of more pixels, and you're more sensitive. So the leap from Spitzer to JWST, and again, you're 1,000,000 times faster than you could do on the ground, is unbeatable. And that's why James Webb is seeing these galaxies at the earliest possible time they could be forming. You can do spectroscopy around dwarfs and of planets and things that were just otherwise impossible with anything else. So that's on the infrared side. On the finding exoplanet side, we've made great advances in our ability to measure the radial velocity wobble of stars. It started out with finding 51 Pegasi, was, hundreds of meters per second of signal from a Jupiter in a fast orbit, to where we're now pushing down to planets a few times the size of the Earth in not quite Earth-like orbits, but, we're getting there. So factors of 100 more sensitivity for the wobble technique. The transit technique pioneered by the Kepler satellite takes advantage of space, not in the same way the infrared does, but when you're in space and don't have an atmosphere, you can measure the signal from a star with a few parts per million precision, so that if a planet goes in front of the star, you have a small dip in the brightness of the star, and you can measure the passage of an Earth going across the face of the star and say, there's the transit of an Earth-sized planet. It's a faint signal, and an Earth in an Earth-like orbit around a star like the Sun, you'd have to measure that 80 part per million dip a couple of times over a couple of years. And the stars were just a bit too noisy themselves for Kepler to do that. But for any planet, that's a bit bigger than the Earth, or in a bit closer, or around a star that's a bit smaller, Kepler and now its successor, the TESS mission, have revolutionized exoplanet science. And in fact, most of the 5,000 planets that we've got confirmed are from Kepler and TESS from the transit technique. And that's been revolutionary from space. Still to come is the European Gaia mission, which is going to finally let astrometry start finding planets. I mean, we tried to build the SIM mission to get down to the level of Earth's, and that would have been worked for a very small number of nearby stars. Gaia is a survey that surveys the whole sky, looking at astrometric wobbles, and it won't do Earth, but it'll do Saturns and Jupiters around stars out to 100 parsecs. So astrometry will find another 10,000 planets. So there's sort of a Moore's law for exoplanets starting from the mid-90s, and the number of planets is doubling every 2 to 3 years.
Yeah, and well, I'm glad you brought up both future missions and the current missions that are next generation that are already up there right now. It's as if everything has converged, right? Especially on James Webb. Exoplanet studies, deep sky surveys, infrared astronomy, and the kind of optics and sensitivity they offer. It's like we can now search for smaller rocky planets that orbit closer to their suns. And now, why are those the ones we really want to find?
Well, if you want to find something that might have life, anything like we know it, you want to have a planet in what's called the habitable zone, or more colloquially, the Goldilocks zone. You want a planet that's not too hot, not too cold. You want a planet that's not too big so it doesn't turn into a gassy giant. You want it so it's not too small so it wouldn't lose its atmosphere. And, that little boundary is you want something bigger than Mars, maybe less than 1.5 or twice the radius of Earth. You don't want it in much closer to its star than Venus, too hot. You don't want it to be much further out than Mars, too cold. And that carves out a parameter space that we're just starting to be able to detect planets in. It's still very hard for any of our existing techniques to actually find an Earth analog. One Earth around a solar-type star is actually a challenge for any of the techniques I've enumerated. So we're pushing on it. The wobble technique hopes to be able to push down to that level over the next decade. Webb's coronagraph won't do that. We have a testbed coronagraph going up on NASA's next big telescope, the Roman telescope. And that has a testbed coronagraph that'll test a lot of the techniques for correcting the imperfections, not through the atmosphere, but the imperfections of the telescope itself, so that you can reject the starlight, which is 10 billion times brighter than the reflected light from an Earth. So you've got 10 billion and one photons coming at you, and you have to get rid of 10 billion of them from the star to get the one from the Earth. And then that's going to be a mission that the National Academy Review of Astronomy said NASA should go ahead and build, something called the Habitable Worlds Explorer. So we're just starting the technology program and the formulation of that, what that mission would look like. First conceptually and then more detailed formulation. And that'll go up sometime in the mid to late 30s. So, and that's where for the first time we'll actually be able to directly image an Earth around a sun-like star, and not just image it, but actually take its light, separate it into its component colors with a spectrograph, and say the atmosphere of this planet has, it shows maybe water, it shows ozone, carbon dioxide, it shows things that might be evidence for life itself. Certainly, you could find evidence of a habitable atmosphere, and maybe depending on what you see in that atmosphere, you could say, hey, there's some sort of photosynthetic process going along, or there's lots of methane. It's the early Earth didn't have an oxygen-rich atmosphere; it had a methane-rich atmosphere. So you'd look at the atmospheric constituents of maybe 10 to 20 habitable Earths. We expect to find, if you surveyed something like 100 nearby stars and search their habitable zones, from what we know from Kepler and TESS and ground-based surveys, maybe 25% of stars like the Sun have an Earth in the habitable zone. And we'd want to go look at 100 of those and say, okay, where are those Earths? How big are they? How hot are they? What do they look like?
Well, you've anticipated my next question, which was, yes, the next generation telescopes that will allow us to refine the search for habitable or potentially habitable planets even further. So, yes, there's the Nancy Grace Roman. There's also the 30-meter class of ground-based telescopes.
Right.
Yeah. And they're also going to have coronagraphs and spectrometers.
Right.
And adaptive optics to correct for all that pesky atmospheric interference. Yeah. In fact, my listeners may recall, we talked about this in a previous episode about how direct imaging studies will be much more possible, much more feasible in the future. So for you personally, I had to ask, given that James Webb is the most powerful and complex observatory that we've ever sent up, and the fact that it's just a groundbreaking infrared astronomy observatory, how excited were you when it finally got off the ground?
That has been a very long process. I mean, I was involved with the proposal team for probably 15 years, going to meetings, listening to meetings, wondering what the budgets were going to happen, watching the cost increases, watching the delays. It was a very long gestation period, but it all is working. So Christmas Day, I was with my family and we watched the launch. And I think the most memorable image from the launch is the satellite, is James Webb drifting away as seen by the camera on top of the Ariane rocket. And you could see the solar panel deploy, which meant that the launch was successful. The spacecraft was going to have power because the solar panels were coming out. And that was a great moment. And then it was followed by 6 months of actually getting the telescope deployed and seeing the first images. And NIRCam was heavily involved with getting all the segments lined up and making sure everything was working. And then commissioning, and now we're starting to take data.
Now, and this is really exciting, in the coming years, Webb is going to be dedicating observation time to Alpha Centauri, star system right next door. And you'll be right there on the ground for that, won't you? Leading a team.
Yeah, so we put in a proposal to the open time solicitation for what's called Cycle 1. And we put in a modest-sized proposal. And it turns out it'll take about 40 hours or 2 days. And we're going to aim Webb at one of the brightest stars in the sky. And it turns out that's actually really challenging because Webb is not designed to look at super bright things. It's designed to look at faint things. And Alpha Cent's really bright. So we have to blind offset from a fairly faint nearby star and jump over to Alpha Centauri to put it right behind the coronagraph of the mid-infrared instrument, and then go between that star and a reference star and subtract out the light from Alpha Cent itself. And also Alpha Cent has a companion, Alpha Cent B, about 8-10 arc seconds away. And that star is really bright. And we have to subtract out its light. And hopefully we can get down and see a planet maybe the size of Saturn, maybe a little bit smaller, maybe a bit bigger, something like that. We don't have the sensitivity to get down to see something like an Earth. We'll have to wait for that for probably one of the big ground-based 30-meter telescopes will do a good job on that. But certainly if there's something the size of a Saturn, we should be able to see it. And I was impressed that the time allocation committee, which was judging, 1,000 proposals, actually took one that was sufficiently high payoff, but also very high risk, and actually accepted our proposal. And so just a little bit, I have a telecon with the team at the Space Telescope Institute to start doing the detailed planning of how we're actually going to make that observation a success. We're actually using the ALMA radio telescope to study Alpha Cent, because Alpha Cent is actually bright enough to be detected at radio waves, but not so bright that it makes it hard for the ALMA telescope to measure it relative to nearby quasars, so we get a very accurate position for Alpha Cent. It's actually hard for optical telescopes on the ground to measure Alpha Cent's position accurately, as it's so damn bright. So we use the radio telescopes to give us a good position. We'll offset from a star to the radio position that we have worked out. Because Alpha Cent's moving very fast, we have all these different motions. It's got a parallax motion because the Earth moves in its orbit, and that changes the position of Alpha Cent. It's got a proper motion, just moving across the sky. Alpha Cent A and B are orbiting around each other. And we have to get all those figured out so that we can point Alpha Cent properly at just the right time to make these observations. So that'll be a challenge. Then we have to get rid of the light of all the Alpha Cent A and Alpha Cent B and any other background stars. And what's left over is hopefully a planet, if there's one there.
It is kind of a cruel and comical fate, isn't it, that this star system right next door to us, a place that has a one sun-like star, reasonably good bet at finding potentially habitable planets, and yet we can't discern it because it's just too bright. That close, but too bright. Luckily, Proxima B now, we're up to 3 confirmed planets there.
Proxima has, at least 2 planets, so that's a good thing. But they're again sort of too faint to be studied with Webb. But there'll be stuff to do. I think the 30 meters may try again. I think they may be orbiting too close to their host star even for the 30 meters. But there'll be lots of stuff to do in the next 20 years. So I'm looking forward to doing all that, or having younger colleagues do it all.
Yes. And so looking at your work in this field, seeing how it went all the way back to the beginning, right? I mean, the first confirmed exoplanet was 1995. You were looking for them back in the 1980s. So is it fair to say you were studying exoplanets before it was cool?
Yeah, we used to have meetings at the American Astronomical Society in the early to mid 90s, and there'd be 5 or 6 of us in the room. We're the only people talking about exoplanets. Now, if you go to a meeting of the American Astronomical Society, which is, a 3,000 plus person meeting, probably a third of the talks, certainly a quarter of the talks, are on exoplanets. So it's remarkable how the field has grown from just a bunch of kids who are too cool for school and people going, why are you wasting time on that? To, oh my God, here's a field that got a Nobel Prize.
And so, having seen the way it's grown, evolved, and become such a big deal there, is that a source of pride or satisfaction at all?
Oh, yeah. But it's also frustrating. I mean, in that, there are just a whole lot of smarter people than me now doing all this work. Because, you got to get all the details right. There's just so much stuff going on. It's hard to keep up. And, I like being sort of in fields where I'm sort of alone with just a small number of people. When you're in that case, you're sort of in the arena. You may not be the best at what you do, but you're the only one doing what you do. And, now you actually have to be really good because there are a lot of people doing it. And it's spectacular young people doing spectacular science with spectacular capabilities. So the field is going to go great for, a very long time to come. What's nice about exoplanets is it's something that's pretty easy to talk about with the general public. They get it. Congressmen, congresswomen get it. The funding people get it. The donors get it. It's easy to say, I'm looking for a habitable Earth. It's harder to say, I'm looking for dark energy or dark matter. It's less intuitive, certainly. All that stuff's important and interesting. I won't obviously take anything away from that. But when you say, I want to look for a planet, your seatmate gets really interested.
Mm-hmm. So, last question now. I have to ask, you were actually in a Star Trek movie, Star Trek V, The Final Frontier. And from what I've seen, you were brought on as a science advisor for the script. But you got a chance to be part of the extra crew?
I wasn't actually in it.
Oh.
I was just the science advisor. I'm in IMDb as the science advisor. I actually got a full screen credit, and that was lots of fun. We were meeting with Bill Shatner, who was directing it as well as obviously starring in it, and worked with the producers and the writers and, helped lay out where they'd be going to the center of the galaxy and so on. So that was a great deal of fun. There was the promise that I could be possibly even in the next movie, but they actually wound up changing producers and writers after Star Trek V and went in a different direction. It was going to be about the Starfleet Academy and Shatner and Spock's early days, which of course that came along as the rebooted Star Trek, 20 years later. Mm-hmm. But I was going to be one of the professors at the Starfleet Academy when that idea was first being sent around. But then with the new creative crowd with Abrams and company, I was long gone by then. But it would have been fun to be lecturing to Spock and Kirk and everyone about habitable planets, which was what I would have been doing. But I was the science advisor, and that was great fun.
Well, I hope an opportunity like that comes back around, because I would definitely pay to see that. I think that would be a real good, science fiction and science fact just come together.
They certainly do.
Well, I wish you best of luck there with the coming Alpha Centauri observations.
Oh, yeah, it's going to be... It'll be, white knuckle that whole couple of days.
And also, yes, looking forward to the future of exoplanet studies. I think it's really wonderful the way things are coming together, and what we've been hoping for, right, for decades. What human beings have been hoping for as long as we've known that there were other planets out there and other star systems out there, right? This is
it's a long term together. Exactly.
Well, and thank you so much for making time for us today and telling my listeners about all this and familiarizing them with this.
Yeah, if you could send me a link to your podcast when it gets posted, that'd be great.
Totally. In fact, this is our third episode dedicated to exoplanet studies.
Oh, great.
Because of course it's just such a rich field.
Yeah, exactly.
And yes, and I hope we can have you back on here with some exciting news, and
I'll tell you about Alpha Cen. Give me about 9 months.
Okie dokie. Perfect.
Okie doke. Talk to you soon.
We'll pencil that in. Okay. Thank you very much.
Bye-bye.
And to those who've joined us here today, I strongly recommend you check out Charles Beichman's extensive list of publications, articles, his long history of work in infrared and other forms of astronomy. Some links will be provided in the episode data. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.